Yeah, hey.
So Christoph is a project scientist at the Advanced Light Source of Lawrence Berkeley National Laboratory. He received his PhD from Bielefeld University in Germany in 2016, where he worked in the field of spin caloritronics. And then he joined the Berkeley National Lab to work as a postdoctoral researcher, and he currently studies investigation of magnetic materials and effect using polarized soft X-rays. So Christoph, whenever you're ready, you can share your screen.
Okay, can you all hear me?
Yes, we can hear you very well.
And can you see my slides correctly?
Exactly, that's correct.
Okay, perfect. All right, then I guess I can start. Yeah, thank you very much for the kind introduction. I'm really excited to be here and give this this tutorial talk. And of course, I would also like to thank the organizers for inviting me to give this tutorial. So in my tutorial, I will talk about how we can use soft X-rays to investigate magnetic properties. So my name is Christoph Klewe, and I work at the Advanced Light Source at the Lawrence Berkeley National Lab in Berkeley. And there I'm part of the Dichroism program together with Dr. Patrick Schaefer and Dr. Alpha Ndiaye. Wait a second. Here. Yeah, and the Dichroism program basically combines 3 different beamlines, which are beamline 402, beamline 631, and beamline 1101. And our main focus at these beamlines is studying the electronic and magnetic ordering phenomena of materials. And to study these effects, we employ a variety of different techniques. In particular, to look at the electronic and magnetic structures, we can use X-ray absorption spectroscopy, X-ray magnetic circular dichroism, and also X-ray magnetic, excuse me, X-ray magnetic linear dichroism. And in order to investigate also spin dynamics and spin current propagation in materials, we can use X-ray detected ferromagnetic resonance. And so in this talk, I want to give you a brief introduction into these types of techniques. But first, before we dive right into the techniques, I think it will be very useful to get a very brief understanding what a synchrotron is and how it functions. So for example, here is a picture, a bird's eye view of the Advanced Light Source where I'm working. And here's like a schematic cartoon sketch of what a synchrotron looks like. Now, in this case, this is not from the ALS, but this is actually a graphic I found from the synchrotron Soleil. But in general, these components are very, very similar in the synchrotrons. And so in general, a synchrotron light source is a circular particle accelerator, and most commonly an electron accelerator that can produce very bright electromagnetic radiation, typically in the X-ray range, but it can also be in the infrared range for some applications. And typically synchrotrons work as or operate as user facilities where scientists from all over the world can apply for beam time, and then they get allocated beam time and can use the equipment at the synchrotron for their studies. And the research interests can include anything from condensed matter physics, material science, biology, medical research, and even to archaeology. Now, we can get a better idea how a synchrotron works if we take a quick look at some of the main components. So in the first stage of the synchrotron, we basically have the linear accelerator, which is shown here. And the linear accelerator is basically a hollow vacuum tube where electron bunches are accelerated between oscillating electric potentials to an initial velocity. So this is sketched here in this little animation that I found online, where here we have the ejection of electrons, and these are then accelerated between these oscillating potentials. And then from the linear accelerator, the electron bunches are injected into the booster ring, which is the second stage acceleration, which is this kind of circular, this ring accelerator here. And that combines linear accelerators and bending magnets to keep the electrons on this ring trajectory. And this ring shape allows the electrons to do multiple cycles in the acceleration, and thereby we can get them to very high energies in the giga-electron volts, so to real relativistic speeds close to the speed of light. And from the booster ring, then the electrons are injected into the actual storage ring, which is this structure here. And this is the third stage, and in the storage ring, the electrons travel with a constant velocity through a number of bending magnets and insertion devices, which both types can generate the X-rays that we then want to use for the experiments. And those X-rays are then emitted and go into the last stage of the synchrotron, which are the beamline branches. And the beamlines then contain the actual experimental end stations where we can do the experiments. Now, the main elements of a beamline are sketched here. And if we go from left to right, here we see the first element in this beamline is basically an insertion device. In this case, it's an elliptically polarizing undulator. And an elliptically polarizing undulator, or short EPU, is basically an array of magnets that can be adjusted, and thereby that allows us to modulate the electron trajectory. And by forcing the electrons on different trajectories, we can then generate X-rays, control the photon energy. And also by forcing different types of trajectories, we can also control the polarization between linear, circular, and also elliptical polarizations. For example, here we have an example what a trajectory could look like if we want to generate linear polarization, and here we have a trajectory where we would generate circularly polarized X-rays. Now, another critical element in the beamline is the monochromator, which is sketched here. And the monochromator basically consists of a pre-mirror, which is here, and a grating, which is here. And essentially, a monochromator functions similar to a prism that you might already have seen. And it helps us to select the energy, a specific energy out of a broader band of energies. And it also helps us to increase the energy resolution down to the range that's required for the experiment. For example, here, basically, if we look at an X-ray absorption spectrum, we can see that this fine energy range is good enough to resolve all the features that we want to see in this X-ray absorption spectrum, whereas if we have a two-coarse energy resolution, we can't really resolve these different features. So we really need the monochromator to increase the energy resolution to a range where we can use it. And then the beamline also contains a number of optical elements like mirrors and slits, and these can be used to focus, to position and the beam, and to define the beam profile. And of course, the beamline also contains the experimental setup, the experimental end station, which can have a number of different components like magnets, microscopes, different detectors, depending on what we want to do. And then, of course, that's also where the sample is positioned for the measurements. Okay, so now that should give you a general idea how the X-rays are generated in the synchrotron and how they get to the sample in the beamline. So in the next step, we are going to take a look at how we can use these X-rays to get the magnetic information via X-ray absorption spectroscopy and via magnetic dichroism measurements. Now, X-rays are used in many different areas, from everyday life, like, for example, medical applications or airport security, to, of course, to scientific research, where we use it for example, for X-ray crystallography, but we can also use it to look at electronic and magnetic structures. And in general, we have to distinguish between different types of X-rays. In general, we distinguish between hard X-rays and soft X-rays. And soft X-rays are typically in the defined as they are in the energy range below 2 kiloelectron volts. And in our case, soft X-rays are especially useful for us when we want to study transition metals, rare earths, and their oxide materials. Like, for example, if we want to look at complex oxide and correlated electron materials, that's where soft X-rays really shine. And that's the reason for this is that soft X-rays are particularly useful, as they show a very high sensitivity to magnetic and anisotropic states in these materials. For example, if we take a look at X-ray absorption spectra for cobalt, and we compare the magnetic signal, for example, here in this case on the left-hand side, we measured the cobalt L edge was measured in the soft X-ray range around 800 electron volt. And we get a very pronounced XMCD magnetic signal from the XMCD. And on the right-hand side, we see spectra from the K edge of cobalt in the hard X-ray range. And we see that the magnetic signal in this case is significantly smaller. So we see that the sensitivity to the magnetic sensitivity of the soft X-rays is about higher by a factor of about 1,000 in the soft X-ray region. Now, to understand where this magnetic information comes from when we are measuring, when we use the soft X-rays, we have to take a closer look at the mechanisms of X-ray absorption. So, as you probably all know, electrons are essentially orbiting a nucleus on different shells with specific binding energies. And when we shine X-rays onto an atom, the X-rays can then be absorbed and transfer their energy to the electron. And now resonant absorption occurs when the X-ray energy is close to a so-called absorption edge, which basically corresponds to the specific energy to lift a core level electron into an unoccupied higher energetic conduction band state. So a process that is kind of sketched here with these different energy levels. And these absorption edges are element specific. So by tuning the photon energy, we can go to the specific absorption edges and basically probe a complex system with element specificity. For example, in this case here, we see a cobalt L2 and L3 absorption edge, and we see these sharp resonant peaks in the X-ray absorption in the X-ray absorption. That's where the absorption edges are. And this element specificity makes X-ray absorption an extremely powerful tool when we want to look at complex system with multiple components, where we want to distinguish between the different components. but even more than the element specificity, due to the fine structure of the specific electronic energy bands, X-ray absorption is not only sensitive to elements, but it's also sensitive to valence states, coordination sites, orbital occupation, and also to spin states. This can be seen particularly well if we take a look at the absorption spectra of different compounds for different elements. So here on the right-hand side, we see the L2 and L3 absorption spectra of iron, cobalt, and nickel. And we can directly see that if we take a closer look at these spectra, we can directly see that for the different elements, we can easily distinguish the different elements by just looking at the energies. For example, the iron L2 and L3 edge have their energies here between 700 and roughly 740 eV. The cobalt is between 760 and roughly 800 eV, and the nickel lies between like 840 and roughly 890 electron volts. And so if we now look a little closer here in the center, where we have the L2 and L3 edge for cobalt, we can see a clear difference if we look at the cobalt metal and the cobalt oxide. And this difference shows that in the cobalt metal, where we basically probe the elemental cobalt, we see this simple absorption peak, whereas if we look at the cobalt oxide, we get this rich multiplet structure in the spectrum. And this is an indicator for the sensitivity to these different valence states, coordination sites, orbital occupation, and the spin states. So this is really useful, or this sensitivity is really useful if we want to resolve electronic structures in a material, but that doesn't give us really any magnetic information yet. And now, so far, these absorption edges, these absorption processes that I've talked about are all independent of the X-ray polarization. However, by using circularly polarized X-rays, we can gain additional sensitivity to the magnetic moments in a material. So the spin resolved density of states in a magnetic material is typically exhibits an imbalance in for the spin up and the spin down states, which is kind of sketched here in this density of states. And this imbalance in the spin up and spin down states, this leads to an asymmetry in the absorption for left and right circularly polarized X-rays, depending on the orientation of the magnetization, which is kind of shown here. So in this case, we shine in with right circularly polarized light and we get a high absorption. Here we have left circularly polarized light and we get a lower absorption. And this effect, this difference between the different absorption for different circularly polarized lights, that is called X-ray magnetic circular dichroism, or short XMCD. And this effect is maximal for a collinear alignment between the photon helicity and the magnetization orientation. So for example, now if we take two different absorption spectra with left and with right circular polarization, and we have a fixed magnetization orientation, which is in this case aligned along the incoming X-ray beam, we can observe pronounced differences in the absorption, which is shown here, for example, for the iron L2 and L3 edge, where we see these pronounced differences at the L3 and the L2 edge. And these differences in the absorption for the different circular polarizations is what gives us the magnetic moment. So by calculating the difference between these two spectra, we can then get the XMCD signal as the difference between right circularly polarized light and left circularly polarized light. And that's where we get the magnetic information from. Now, of course, alternatively, we can also measure not by switching the polarization, but we can also measure with a fixed polarization and instead switch the magnetization orientation. And the reason for this is that the XMCD signal is proportional to the vector product of the polarization vector and the magnetization vector. So it doesn't really matter which of these components we alternate. We just have to alternate between parallel and anti-parallel alignment between these two. Now, there are multiple different detection mechanisms to measure the X-ray absorption, which are kind of sketched here in this cartoon. So one of the very common methods to measure X-ray absorption is to measure the total electron yield, which basically collects the drain current from excited photoelectrons. So this method is surface sensitive due to the limited escape depth of the electrons, and typically probes a couple of the first couple of nanometers, typically something like the first 5 nanometers of the sample. We can also measure the fluorescence yield from the sample, which is basically generated by the de-excitation of the excited photoelectrons. And in contrast to the total electron yield, this technique or this method is bulk sensitive. So actually can provide us with some different information than the total electron yield. Alternatively, we can also measure the luminescence yield, and which measures which collects the luminescence from a subjacent substrate behind the film. So basically, we transmit the X-rays through the film, and then we measure the luminescence from the substrate underneath. And again, this technique is bulk sensitive, but of course, this requires that the films are grown on a luminescent substrate. Additionally, we can also directly measure the transmission, the X-ray transmission from by looking at the transmitted directly looking at the transmitted X-rays through the thin film, but this requires a more complex sample preparation, as we need very, very thin films for this. But in many cases, it can be very useful to actually combine multiple different methods and measure multiple different detection methods simultaneously, because this can give us a more comprehensive look at the sample and can give us, for example, we can gain surface and bulk information. For example, that was done here in this experiment, where we actually looked at the electron yield at the iron edge from a material, and we looked at the fluorescence yield at the iron edge. And as you can clearly see here in the absorption spectra, we see quite pronounced differences, and we also clearly see in the XMCD signal quite pronounced differences. And this points towards oxidation at the surface of the sample with low magnetization, and but a strong magnetic effect in the bulk of the sample. Now, to give you another interesting study or another interesting example how we can use XMCD here in this study with our collaborators from Bielefeld University in Germany. We used XMCD to study manganese, iron, germanium thin films with perpendicular anisotropy. And these films exhibit a soft and a hard magnetic phase. And by using X-ray absorption spectroscopy and XMCD, we were able to show that the manganese sublattices exhibit a ferrimagnetic coupling, and that so this can kind of be seen here by this up-down structure in the XMCD effect at the L3 edge. And at the same time, we see that the manganese and the iron sublattice are coupled ferromagnetically to each other. Further, we were able to determine the total magnetic moments of the two magnetic species in the hard and the soft magnetic phases by using the sum rule analysis. So in general, XMCD was is a very useful tool to look at different elements in a complex system and distinguish between the different contributions here. So far we have seen that XMCD is proportional to the vector product of the polarization vector and the magnetization vector, and that basically means that the XMCD signal is proportional to the expectation value of the magnetization, and therefore XMCD is sensitive both to the strength of the magnetization and to the direction of the magnetization, and that makes it the ideal tool to probe ferro or even ferrimagnetism in ordered system. Now, alternatively, we can also use linearly polarized X-rays in terms of X-ray magnetic linear dichroism, or short XMLD. And this is kind of sketched here what that can look like. And in contrast to the XMCD, the XMLD is actually sensitive not to the expectation value of the magnetization, but to the expectation value of the square of the magnetization. And that means that the XMLD is not sensitive to the direction, but is sensitive to the axis of the magnetic moments. And therefore XMLD is that makes XMLD a really unique tool if we want to, for example, look at antiferromagnetic order. For example, as in an antiferromagnet, the expectation value of M can be 0, but M squared doesn't have to be 0, or can be finite. So in this case, that makes XMLD very useful for these kind of studies. And again, similar to XMCD, the XMLD can be measured by taking two different absorption spectra. So though in this case here, we switch between parallel and perpendicular coordination between the polarization vector and the magnetization vector. And the XMLD is then calculated as the difference between the parallel and the perpendicular spectrum. And again, we can distinguish between two different measurement configurations. For example, here on the left-hand side, we see this geometry XMLD type 1. And XMLD type 1 basically corresponds to switching the magnetization while measuring with a fixed X-ray polarization. And this is very useful if we need to eliminate non-magnetic contributions, like, for example, a natural linear dichroism, which can also show up. And the second type, XMLD, corresponds to a measurement with switching the polarization and keeping the magnetization fixed. And the advantage of this geometry is that it doesn't require any magnetization control. So this is ideal if we want to look at antiferromagnetic order. Yeah, to give you another example of how versatile XMLD is and how it can be used, I want to highlight this one study that we have done with Professor Zhuang Chen from the Harbin Institute of Technology. And in this study, we used XMLD to look at the antiferromagnetic spin structure of 110-oriented bismuth ferrite. And by measuring a temperature series, which is shown here, we were, by measuring a temperature series of the XMLD, we were able to observe that the magnetic ordering, the antiferromagnetic ordering in this material vanishes above, roughly above 650 Kelvin, so which we then determined to be the Néel temperature in this material. And furthermore, we also investigated different strain states of this bismuth ferrite on different substrates via angle and polarization dependent X-ray absorption studies. We found that the antiferromagnetic axis can be tuned from in plane to out of plane via the epitaxial strain. So now, so far we have looked at the X-ray absorption spectroscopy measurements, and I've shown you that allows us to study static magnetic ordering phenomena with element side and valence state specificity. But now in the second part of my talk, I want to introduce the technique of X-ray detected ferromagnetic resonance. And this is a very exciting new technique that also allows us to not only measure static magnetic interactions, but also allows us to look at spin dynamics based on the same mechanisms as XMCD. But before we, they don't actually create a continuous X-ray beam, but in fact they emit short X-ray pulses. So we actually generate a beam structure that has that is like an X-ray pulse structure. And at the advanced light source where I'm doing most of my experiments, these X-ray pulses have a frequency of 500 megahertz. And then what XFMR is, we first basically need a general understanding of how ferromagnetic resonance works. So basically, ferromagnetic resonance, or short FMR, describes the excitation of a magnetization of a material into a precessional motion using a microwave excitation. And the response of the response can then be measured in the power absorption of the excitation signal of the microwave. And this response is most pronounced at the precession frequency of the material, which is typically in the gigahertz range. And what this looks like in a measurement is shown here. For example, here in this case, I have measured ferromagnetic resonance in permalloy with a frequency, with an excitation frequency of 2 gigahertz. And here we see in the absorbed power, we see this pronounced peak, this pronounced ferromagnetic resonance peak at the precession frequency of the material. And from the properties of this resonant excitation, like for example, the line width and the position of the resonance field, we can then determine different properties of the material, like magnetic anisotropies, damping, and dissipation mechanisms. But we can also use this excitation, this microwave excitation in FMR to generate spin dynamic, or to generate spin excitations, spin waves, and spin currents. But like many techniques, ferromagnetic resonance basically only measures the average signal of a sample, but cannot really distinguish between different components in a complex material. And that's why XFMR is such a powerful tool. So basically, XFMR is the combination of ferromagnetic resonance with X-ray magnetic circular dichroism, which we here use as the detection mechanism of the spin excitation. And combining these two different techniques, we are able to probe spin dynamics in a magnetic material with the element side and valence state specificity of X-ray absorption. Now, here's what that looks like in detail. So in an experiment, basically, we basically have the sample mounted on a coplanar waveguide with the magnetization aligned along the waveguide by an external bias field. And then the magnetization is then excited by a gigahertz pump signal into a precessional motion, which is kind of sketched out here. So the microwave at the coplanar waveguide generates an RF magnetic field at the sample position, and that generates this precessional motion, this excitation of the magnetization. And this microwave excitation has to be synchronized to the frequency of the X-ray pulses. And if that is the case, then we can use the X-ray pulse structure to probe the phase-dependent components transverse to the static field. And this measurement is stroboscopically. So since the XMCD is sensitive to the magnetization, we're actually not probing like the static components like we do in regular XMCD experiments. But here, if we shine in like this, we are actually able to probe these components like the components of the in the magnetic precession that are transverse to the static field. And now by modulating the phase of the microwave excitation by 180 degrees, we can then probe opposite sides of the magnetization precession. For example, that is shown here, where here we basically probe the parallel component, and here we probe the anti-parallel component of the precession. And that is achieved by modulating the phase of the initial microwave excitation. And we can understand why we then get this magnetic information if we compare this to the X-ray absorption spectra, and we compare the two different states to two different absorption spectra. And then we can see here that we are actually probing this difference in the X-ray absorption. And the XFMR, or we can also call it the dynamic XMCD, is then calculated, or is then basically the difference between the state parallel, or the intensity plus, and the state anti-parallel, the intensity, the negative intensity. The way we can then measure this, or is basically we can map the entire spin precession by shifting the phase delay between the RF excitation and the X-ray pulses. That is, for example, shown here in these phase delay scans. And what that means is that each point of phase delay scan corresponds to a different state in the precession of the magnetization. For example, here we look at this state, and then we shift the phase delay of the RF excitation, and then we look at this state, and then we look at this state, and that gives us this pronounced shape in the phase delay scan. And now if we take multiple phase delay scans at different fields across the ferromagnetic resonance of a material, we can then extract the amplitude and the phase information of the entire magnetization precession from these scans, which is shown here. Here, for example, in the amplitude, we see this this pronounced ferromagnetic resonance peak here, and in the phase we see the sigmoidal shape, which is common for an excited oscillation like this. Now, yeah, I think I still have a little bit of time. So now to give you some brief examples what that can look like in experiment, and how we can then use XFMR. Let's take a look at this study, which we have done together with Professor Shu's group from UC Berkeley. And in this experiment, we investigated the spin current propagation through an antiferromagnetic insulator, in this case cobalt oxide, from a spin source to a spin sink layer. So basically, we looked at this kind of multi-layer structure, which consists of this permalloy spin source layer and this cobalt ion spin sink layer, and we have a spacer layer consisting of some thin silver films, and in the center we have this antiferromagnetic insulator cobalt oxide. And then by using both the ferromagnetic resonance condition from the ferromagnetic resonance and by using the element specificity of the XMCD, we are then able to excite a spin current in the permalloy source layer and then individually measure the different elements and individually probe the response in the cobalt ion sink layer. And the results from this are shown here for two different thicknesses of the silver spacer layer. And here we have the amplitudes and the phases. By analyzing both the amplitude and the phase for these for the different layers, we were able to observe that in this structure, a coherent AC spin current is generated in the permalloy and can actually be transmitted through the cobalt oxide, the antiferromagnetic insulator, into the cobalt ion. And furthermore, by taking a temperature series, we were also able to show that this coherent spin current transmission through the cobalt oxide is enhanced around the Néel temperature of roughly 260, 270 Kelvin of the cobalt oxide, which is a really, really interesting result. And since I'm running out of time, or since I'm getting closer to the end, I'm just going to give you one short another example, and this is basically a very similar experiment. In this case, again, we have a spin source and a spin sink layer, and in this case, we are looking again how the spin transmission, the spin current transmission through an antiferromagnetic insulator works. In this case, however, we looked at nickel oxide, and here we looked at the thickness dependence of the nickel oxide. And again, in this experiment, we found that a coherent AC spin current can be generated in the spin source layer and can be detected in the spin sink layer, and thereby is able to propagate through the antiferromagnetic insulator. And specifically, we found that from the thickness dependence that the spin current transmission is enhanced through the antiferromagnetic insulator, is enhanced for a thickness of the antiferromagnetic insulator of around 2 nanometers. And this again was a really quite interesting result. And yeah, and with that, I would like to come to my summary and would like to yeah, take a look back. So in the first part of my talk, I have talked about about X-ray absorption spectroscopy, and I have shown you how we can use X-ray magnetic circular dichroism and X-ray magnetic linear dichroism to investigate magnetic ordering in materials, and how these effects are element, site, and valence state specific, and therefore are really powerful tools to look at complex materials and different components in complex materials individually. And in the second part, I have introduced X-ray ferromagnetic resonance, or XFMR, and I have shown you how we can use X-ray absorption to probe spin dynamics and spin currents in complex materials. And I hope I could convince you that these techniques and soft X-rays are a really powerful tool for studying magnetic interactions. And with this, I just want to point out one last thing. So if you are now interested in using X-ray absorption spectroscopy and using any of these effects like XMCD, XMLD, or XFMR for your studies, you can apply for beamline at the Advanced Light Source. And we actually have a submission deadline for new ALS proposals coming up at September 1st. And you can find more info under als.lbl.gov. And with this, I would like to thank you very much. I think we can open for questions.
Thank you, Thank you for this amazing tutorial. It was really great, and we appreciate you made it accessible to a diverse audience, such as the one of this conference. So we are now open for questions. We have a few minutes left. So I encourage you to raise your hand, your virtual hand, and we can unmute you and ask a question. Alternatively, you can type on the chat. So I think, Luis.
Hello, Christoph. Thank you for a very nice talk. I'm interested in the X-ray detected for magnetic resonance in the example that you gave on the antiferromagnet, the nickel oxide and cobalt oxide. So you're using the nickel oxide as a mediator to see the spin current that reaches the cobalt iron, right? Is it right?
That's right. So we generate, yeah, that's right. We generate a spin excitation in the permalloy layer in the nickel iron, and then we basically take a look at the we look at the response from the zinc layer, the cobalt iron, and so basically by that we basically see how much of the spin current can pass through the antiferromagnetic insulator. Yeah.
Okay, and do you know why is the maximum at 2 nanometer? Is there
no, that's actually that's a good question, and that's still something that we are looking into. So different there are different theories what could cause that, and naturally, I would have expected that if we put an antiferromagnetic insulator in between this as a spacer layer, we would get a lower transmission of spin current. But here we see this enhancement around the roughly 2 nanometers. I could only speculate on different effects. It could have something to do with a better interface transition. But it is not entirely clear yet why we see this.
Great. So you're planning to try like a G something, for example?
We haven't tried that with YIG yet. No. I know that there are experiments not with X-ray ferromagnetic resonance, but there are experiments that use DC methods or electronic measurements and look at the inverse spin Hall effect in platinum when they excite a spin current in the YIG, and they also see an enhancement for very thin nickel oxide layers. They also see an enhancement of the spin current transmission in those systems. But we haven't done any. We haven't tried anything with YIG yet.
Okay. Can I continue with
I have a question as well, but I think
okay, go ahead.
So with this X-ray absorption, can you modify intrinsic interactions, effective interactions of your magnet, like Heisenberg or spin orbit, the Dichroism? Is this something you have tried?
Sorry, can you say that again?
So modify interactions inside your magnet, like modify or induce effective Dichroism interactions. Also,
you're saying by using the X-rays as
exactly
as an excitation. I'm actually not sure if that would work. That's certainly not something that we have tried yet. So we really mostly use the X-rays as a probing mechanism. But that's certainly something interesting that one could look into. And I have no good idea also what intensities one would need for that.
Yeah, I understand. So we don't have questions, but I see that the audience has more. So we do encourage you to visit Christoph in Gathertown, and I'm gonna paste the link here. So he will be here for some time. So please visit Christoph, he will be there, and we can continue with the next speaker.